So it's my privilege now to introduce our next speaker, Myshkin Ingawale, who co-founded Biosense, which is an internationally recognized med tech company designing and building innovative, disruptive healthcare technologies. He holds a PhD in management information from Calcutta and a bachelor's in electrical engineering from the National Institute of Technology in Bhopal. He's been part of some really interesting projects, including the Copenhagen Wheel, which is an novel electric bicycle, to a blood test that works without blood, that has helped do things like reduce deaths from anemia. So I'm expecting to see some wonderful transformative technologies from you, and I'll yield the floor. Thanks.
Thanks for the very kind introduction. It was the last time I was on stage, I was introduced as an idiot. But I'm serious. The name Myshkin is from the novel called The Idiot by Dostoevsky. Anyway, so wonderful to be here, and a privilege to follow three great speakers. What I've decided to do is just sort of tell you two stories, which sort of go with the theme of engineering plus medicine. Most of the first story would be my own story, how I stumbled across a few of these projects. And the second is of Biosense, the company who is building some of these technologies which we referred to. So this is the Copenhagen Wheel. It's an electric bike, which I was working on 5 years ago. It's an interesting concept where the rear wheel is actually the bike. It has a electric motor, batteries, controller, everything which you need in an smart electric bike sort of crammed into the rear hub. This vision was by a professor at MIT under whom I worked. His name is Carlo Ratti, and eventually, I mean, the bike got built, it became a startup and so forth. I'll ramble through a few of these projects. Maybe there's a little intersecting thread here I think you may notice. This bike was unveiled at Copenhagen, hence the name Copenhagen Wheel. So meanwhile, I was also trying to finish off my PhD, and one of the biggest areas I was interested in is how, which was referred to in the last talk, how crowds can come together and create something of value. In the specific case of Wikipedia, we know, despite various inaccuracies and inconsistencies and so forth, there is still substantial value. And one of the big questions I was trying to figure out was, at that scale, how do you find quality? How does quality, whatever it is, what does quality mean? How does it emerge? And most importantly, how can quality sustain itself over a period of time? So luckily for me, in case of Wikipedia, you can measure this quite well. You can download the revision history of all of Wikipedia. So you can look at every single edit ever made and try to figure out what's happening. What I did was build something called a Bipartite Network. So a network in which you have articles and users represented as nodes. And the connection between articles and users is the link. So that's how you form the network. And you can figure out a bunch of stuff if you really analyze the properties of this and the structure of this network. So this whole PhD was sort of an intersection between one is, of course, information systems. The other, surprisingly, was epidemiology. How does something spread in this network? So that's my first sort of stumble across story. It was good enough for me to get me out of there with a PhD. My wife was especially happy. And she said, that why don't you now get a real job? Which I did. So I worked in consulting for a while and I learned a few other intersections around how these fields interact with the real world of business. And in doing so, I stumbled upon my third, the second part of my talk, which is going to be the story of Biosense. So a few doctor friends of mine in India were solving like really big problems over there in primary health. So they were trying to figure out how to reduce maternal and child mortality in areas where there was like really big resource constraints. So low resource settings, lack of doctors, lack of infrastructure, and all of that. So we ended up building something called TouchB, which is a non-invasive anemia screening tool. This was like sort of a big thing when it came to those kind of geographies because, like I said, in the absence of pathology labs, in the absence of qualified medical personnel, it was important to have something which could be taken to the field and used by relatively low-skilled healthcare sort of volunteers. So this is what got Biosense started. We built this, by the time, like I said, I'd been a consultant, so I could draw boxes in PowerPoint and Excel, and the Excel stuff had graphs which went upwards, so we got a bunch of investors who were also happy to be part of our story. So Biosense got started, and we realized that we were onto something. We had these two big words at the back of our mind: democratize healthcare. I don't know exactly what it means, but in India, we meant very, very simply. We knew that the actually simpler word to make this happen was access. When we went to various clients, which are like clinics, hospitals, government centers, who used to buy our stuff, they told us that, what else can you do? Tell us what else do you have which can solve our problems. So one of the things which we again stumbled upon was that urine analysis, so long neglected child of pathology. So this machine here is an automated urine analyzer. One of the interesting ideas which came up is that, hey, why don't we take a very simple urine dipstick, reagent stick like this, which can measure 8, 12 parameters in urine, or any other reagent. You can use the different variants of this for different parameters. So why don't we use this as a way to really sort of take healthcare where it doesn't really exist today, at least take diagnostics where it doesn't exist today. So the challenge in front of us was very simply that how do we make that automated urine analyzer possible in a setting where there was no power, no qualified doctors or lab techs and so forth, and how do you make it usable? How do you make the data usable? So basically, what is the best way to build an advanced electronic device that has high quality imaging, data processing, communication, and interfacing capabilities, all of this, right? And after a few interesting prototypes in the lab, we suddenly realized that the answer was actually right here in our pockets, this one. It's a phone. Basically, all of this stuff is what your own phone does. So we started figuring out how could we use a smartphone to do urine analysis. And this is how you can actually do it. So we built an app which, with the help of a small peripheral, the illumination chamber you see there, is just very simply using a series of images in that controlled lighting setting, able to measure up to 15 parameters, which we can sort of, you can see there, are possible to view in the app. It goes onto the cloud. And of course, once it's in the cloud, you can do very, very smart things with that data. So this is a very simple contraption, is something we built as a substitute for otherwise relatively expensive, complicated, hard to buy and hard to use equipment in that kind of low resource setting. So basically, it was as accurate, it was cheaper, it was better in some sense because the data is now much more powerful. The phone could tell non-doctor staff in the field a bunch of stuff which they could take action on. And because the data is in the cloud, the patient could also access it, the head office could access it, and there are a few interesting stories that I can come to if we have time. Basically, using something which was otherwise, I think, simple from an engineering perspective and simple from a medical perspective, but just this intersection created something which was valuable to a real-life patient, a real-life clinic system, a real-life a government system in parts of India. So this is some screenshots from the app. So you can actually use this quantified data in many interesting ways, starting from very simple trends to more complicated. Once, of course, like I said, it's in the cloud, you can do lots of more complicated stuff. Interestingly, and this is a small example I can give, might be sort of, again, I said stumble upon it. So one of the interesting applications we stumbled upon was not medical, not engineering, but a human kind of real problem which was faced by government systems in India. So the health ministries, the people who employ these health volunteers, these contractors, et cetera, who do these kind of these kind of surveys, who do the even health camps in remote parts of India, come across a very specific problem of corruption. They have cheating, essentially, people who cheat them and they don't have real data. So very simple kind of system like this, which relayed all the data to the cloud, which can be viewed on a map in almost pretty much real time. How many tests are being done where, what are the results, you can basically avoid a lot of the very practical problems which a program officer might come across when trying to roll out something like this. So we sort of learned a few of these things on the fly, what works, what doesn't work, and managed to create something, like I said, of value using relatively simple building blocks, both on the engineering and medicine side. Of course, very interesting, I'm a data guy, so what really interesting from my perspective was that once you had all this data on a server, we use Azure, which is a cloud-based service. So we could actually provide a lot of other interesting analytics, a lot of other interesting insights based on this data to both the patient and the healthcare provider. So just a few, again, stumbles. This is a very simple, like I said, a system which just uses a basic Android-based device and a very cheap peripheral, which we built in India. And so once we had this, again, just to stumbling more forward, once we had this basic system, we could innovate further on the chemistries. So do more interesting things like albumin to creatinine ratio and a few other possibilities which came up over the last 3 years, where once this platform existed, we could use the same kind of basic infrastructure to offer more tests, offer more services based on additional chemistries which we developed with universities in India. So basically my whole thesis here is that stumbling across from, once you have this basic thesis that you have one strand of value which you can offer to a customer, you can just keep building on that and let things go where they can. So I don't know if that's making a lot of sense. I'm assuming in your cases also you've seen something similar, where once you have something which is really useful, you can, rather than very top-down approach, use a day-to-day kind of observational method to come out with additional sort of ways to make a better use of what you already have. So that's it's called UCheck, the system. So while doing all this, that's the Biosense sort of stumble story. Interesting thing which I found is that now I'm no longer full-time with Biosense. I'm an advisor to them and a few other ventures in India. One of the interesting things I found is happening in this space is that, of course, you all know the whole mobile phone story and cloud, how both of these together can unlock a lot of interesting possibilities. The second thing which yesterday I was fascinated to see was this whole revolution which is happening on the hardware side as well. So 3D printing. So even in our case, once you have understood the basics of a mobile phone platform, software, you can, using very simple peripherals, do a lot of stuff. So processing, imaging, everything which is possible on a phone, you can now amplify using physical real stuff, which you can build, prototype, iterate, and get to where you want it to go. So just a quick illustration of, so we had 2 RepRap machines in our office. These are very, very basic 3D printers, which we could, in our very early days, still use to sort of build stuff, which, so I'm assuming since many of you might have been there yesterday, so just to give the basics of this, there's a 3D model, which is a software model, and then you convert it into a real physical prototype. So this basic method, we found we could use even in a very low sort of not capital intensive lab in a startup environment. So just a short video there from a friend of mine who makes this right next to our office. So these machines we could use to very quickly, over a period of these 3 years, iterate on some of the interesting ideas which we thought could be useful, and very quickly take them to field and start figuring out which worked, which didn't work. So none of these are actual medical technologies, but just to give you an idea, I think if I'm not wrong, this is Walter White's head. So what I found very interesting is that even people who are otherwise not mechanical engineers or industrial designers could grasp this and very quickly convert their ideas into look and feel prototypes, which could then be used to communicate in a larger team to get the conversation going, all of that. So we stumbled, and we continue to do every day, stumble across many interesting things just by the process of trial and error, and a lot of error, but a lot of trials as well, because we could use very cheap prototyping technologies like these. So right now I'm also doing a few other things, mostly in the mobile industry as well in India, where a lot of this probably intersection between software and rapid prototyping technologies, which are getting more and more accessible, will hopefully yield many more crowdsourced or very decentralized way of innovating pretty much as close to the problem as you can get when these kind of technologies are accessible to engineering students, medical students, entrepreneurs, as well as, of course, the big labs. So that's my friend's startup. Anyway, so I hope I could share some interesting stories and hopefully I'll hope to interact more with you over the coffee breaks. Thank you.